In this work, we present Generative Pretrained Controllers, GPC, a physics-based generative policy that learns a transferable discretized latent representation of diverse motor skills from large-scale human motion data. Our framework consists of three stages. We first train a discrete tokenized representation of motor skills using end-to-end RL. We then train a GPT-style generative controller to produce sequences of tokens that yield diverse, naturalistic behaviors. Once trained, the generative controller can be fine-tuned and adapted to a wide range of downstream tasks. In first stage, we leverage finite scalar quantization to train a discrete representation of motor skills. Given a sequence of target poses from a reference motion, an encoder maps the target motion to a discrete code, which are then provided to a controller to produce actions for the character to imitate the target motion. A key design decision is that the whole model is trained end-to-end through reinforcement learning using a deep mimic-style motion tracking objective. This allows the latent codes to be explicitly optimized for robust physics-based control. Our tracking-based quantization can effectively scale to large motion datasets with near-perfect reconstruction success rate, without sacrificing reconstruction quality. Our model can accurately reproduce highly dynamic behaviors, such as flips, handstands, and cartwheels. Once the discrete latent representation has been trained, in the next stage, we train a generative prior to model temporal dependencies between the FSQ codes to generate natural lifelike behaviors. The prior is modeled by a GPT-style autoregressive transformer. The transformer is trained to predict sequences of latent codes through supervised next token prediction. Once trained, token sequences generated by the prior model are used by the FSQ controller from first stage to produce diverse and natural behaviors. Our generative controller can generate a wide variety of diverse and human-like behaviors. By modeling the distribution of natural behaviors, our generative controller exhibits lifelike emergent behaviors, such as responding to perturbations and automatically recovering from falls. The pre-trained model provides a versatile base that can be adapted to various downstream tasks through parameter-efficient fine-tuning. This enables effective and sample-efficient learning of new tasks. We experimented with a set of supervised fine-tuning and RL-based fine-tuning techniques. We first fine-tune our GPC to a gamepad steering task using only one example motion clip. In this steering task, the character must move while following both pelvis velocity and pelvis-facing commands. The behaviors embedded in our pre-trained controller enables the character to generalize and produce natural behaviors for all combinations of commands, which go well beyond what was shown in the seconds-long example data. By fine-tuning GPC with different stylized motion clips, we can adapt the controller to perform the same steering task, but in a different style. Here, the character learns to walk in a combative crouching style, using only one example motion clip of 20 seconds in length. In this trajectory-following task, the behaviors learned by the pre-trained generative controller enable the character to robustly recover when subjected to external perturbations. Here, our pre-trained GPC is fine-tuned with a few spinning and walking motion clips to perform the trajectory following task again, but in a style of walking while spinning. In this task, the character is asked to reach target root positions in 2D. We again post-train the GPC model with a small example motion dataset, which is 1 minute in length. The behaviors learned by the pre-trained generative controller enables the character to perform natural transitions and agile movements in all directions. Here we fine-tune the pre-trained model for the same target-reaching task, but with crouching motions as example data. We push the character around with perturbation forces unseen during training, and the character is able to recover and then proceed with the task. Beyond locomotion tasks, GPC can be also efficiently fine-tuned to perform dynamic maneuvers, like jumping across irregular scenes. Fine-tuned GPC policy can robustly traverse across such platforms while directly following user controls from a gamepad in real time. Our model can adapt to randomized terrains with varying sized gaps and platform heights. Our GPC can also be efficiently fine-tuned to crawl under barriers of varying heights. By sampling skills codes from the latent distribution, GPC can produce more diverse behaviors when performing a given task than baseline methods. Our FSQ tokenizer outperforms VQVAE-based methods when scaling to large motion datasets with highly dynamic motions. End-to-end RL training of the tokenizer enables our model to more effectively reproduce a large corpus of behaviors, compared to a non-end-to-end model, FSQ-K. Our FSQ controller achieves comparable performance to an MLP controller, which does not contain a quantization bottleneck serving as an upper bound for evaluation. To demonstrate the scalability of GPC, we apply our framework to train a generative controller on a large diverse motion dataset, containing over 600 hours of motion data. Here, the pre-trained controller can generate diverse human-like behaviors, including locomotion, gestures, exercise, and acrobatic motions. GPC can also be effectively trained on datasets of different scales, as well as characters with different morphologies. Here we showcase two models trained respectively on the large in-house dataset and on the much smaller Laughing dataset. Both models are capable of generating realistic recovery behaviors when subjected to external perturbations. We adopt a simple token grouping method to balance between context length of the transformer and vocabulary size. Within reasonable memory constraints for the vocabulary size, we observe that a higher grouping factor tends to encourage more expressive and diverse generations. Our FSQ supports skill composition via latent code interpolation. For example, interpolating between punching and kicking produces a motion that performs both at the same time.